6.2 trigonometric equations. So today we're going to talk about solving trigonometric equations. So one method is a linear method. So we want to solve the equation 3 tan theta minus the square root of 3 equals 0. And we're going to solve first over the interval of 0 to 360 degrees, and then for all solutions. So we have 3 tan theta minus square root of 3 equals 0. So we can say 3 tan theta equals the square root of 3, and then divide both sides by 3. So we have tan theta equals the square root of 3 over 3. Alright, so tangent theta is positive in quadrant 1 and quadrant 3. Alright, so first I'm going to work in quadrant 1. So tangent theta is y over x. Okay, so y would be 1, and then x would be square root of 3. So remember that this is the same as 1 over the square root of 3. Okay, and then this is our 30, 60, 90. So our radius is 2. And this angle here is a 30-degree angle. Okay, so that means our angle here, so if 30 degrees is our reference angle, then our angle in quadrant 3 would be 180 degrees plus 30 degrees. So 210 degrees. So 30 degrees and 210 degrees would be the two answers for the interval 0 to 360 degrees. Okay, for all solutions, so we're not restricted to 0 degrees and 360 degrees, a period for tangent okay, so period is 180 degrees or pi. So that means that all solutions would be 30 degrees plus 180 degrees times n, where n is any integer. Okay, so note that we don't have 210 degrees included here because it'll be included if n is 1. So if n is 1, then we have 30 degrees plus 180 degrees, which is 210 degrees. Okay, and then this will list any solution as we circle around the quadrants. The next method is a zero factor property method. So we want to solve cosine theta times cotangent theta equals negative cosine theta over the interval 0 degrees to 60 degrees. Okay, so notice, just like in the previous problem, we have 0 degrees to 360 degrees, which means our answers are going to be in degrees. Alright, so for the zero factor property, we want to set our equation equal to 0. So we have cosine theta times cotangent theta equals negative cosine theta. Alright, so I'm going to add cosine theta to both sides so that I can set it equal to 0. So I have cosine theta times cotangent theta plus cosine theta equals 0. The next thing I want to do is to factor. Okay, so we're going to factor a GCF. Okay, so our GCF here would be cosine theta. So I have cosine theta times cotangent theta plus 1 equals 0. Alright, so this is where the zero factor property method comes in. So the zero factor property says that if we have A times B equals 0, then either A equals 0 or B equals 0. So we're going to set each of these factors equal to 0. So we have cosine theta equals 0, and then we have cotangent theta plus 1 equals 0. Okay, so we want to solve for theta, so we have, we're going to use the inverse functions. So cosine theta equals 0, we can say theta equals cosine inverse of 0. Okay, so for cosine to equal 0, we're going to be on the y-axis. Okay, so x equals 0, y equals 1, r equals 1, x equals 0, y equals negative 1, and r equals 1. So remember that cosine is x over r, so both of these cases we would get cosine equals 0. So this would be theta is equal to 90 degrees and 270 degrees. Over here we have cotangent theta plus 1 equals 0, so we can write cotangent theta equals negative 1. Alright, well, cotangent is negative in quadrants 2 and quadrant 4. Alright, so then we can say, we can use our inverse function. So remember when we're doing cotangent, so I'm going to write theta equals cotangent inverse of negative 1. So remember that we can use tangent when we're trying to plug it into the calculator. We can use tan inverse, but the rules for cotangent is that if your argument here is less than 0, then you have to use 180 degrees plus tan inverse of 1 over x. Okay, so we're going to have theta equals tan inverse of negative 1 over 1, so that's just going to give me negative 1 plus 180 degrees. Okay, so theta is going to equal negative 45 degrees, so that's tan inverse of negative 1. Okay, and negative 45 degrees would be in quadrant 4, but for cotangent inverse, we need to be in quadrant 2. Okay, so we add the 180 degrees, and we get 135 degrees, which is an answer in quadrant 2. Okay, so this is our answer in quadrant 2, but we're talking about cotangent theta here, and so we are also in quadrant 4, so we have to find an angle with the same reference angle as 135 degrees. Okay, so cotangent also has a period of pi, so if we add 180 to 135, so 135 plus 180, we'll get 315 degrees, which is the angle in quadrant 4. Okay, so our solutions, we have 90 degrees from here. We have 135 degrees. We have 270 degrees, and we have 315 degrees. Okay, so any of these 4 angles will make this equation true. Okay, the next method is quadratic method. Okay, so remember what linear and quadratic means. So linear here, we do not have any exponents. Quadratic method, we do have an exponent of 2. Okay. Alright, note that the interval that we are given is in radians. So that means that our answer should be in radians. Okay. It also means that you should have your calculator in radians. So the first thing we want to do is factor. Okay, so this is just simple college algebra factoring. If you want to make it easier to look at, if we just call x, we just call sine x x here, we can look at it as 3x squared minus x minus 2 equals 0. Okay, and then that factors into 3x plus 2 times x minus 1 equals 0. Okay, so we're going to use this to rewrite. This is sine x, and this is sine x. Okay, so I'm going to rewrite this here. This is 3 sine x plus 2 times sine x minus 1 equals 0. Okay, then we use the zero factor property. Okay, so the zero factor property, we set each factor equal to 0. So we have 3 sine x plus 2 equals 0. And we have sine x minus 1 equals 0. Alright, so let's solve the first one. So we have 3 sine x equals negative 2. Or sine x equals negative 2 over 3. Alright, so if we want to solve for x, we can use sine inverse. So x equals sine inverse of negative 2 over 3. Okay, so if I plug this in my calculator, change my mode to radians, so I have sine inverse of negative 2 over 3. It's going to give me negative 0.729728. Okay. From here, we use this as our reference angle. Okay. So notice that this negative angle is not in 0 to 2 pi. So we need to use this as a reference angle to find values that are between 0 and 2 pi. Alright, and then we're going to go back and use this information here. So sine x is negative in quadrant 3 and quadrant 4. Okay, so that's the two quadrants that we need to look at. So if we are looking in quadrant 3, and this is our reference angle, okay, we are going to want to do pi, or 180 degrees, which is pi, plus this reference angle. Now you're not going to use the negative, you're going to use the positive value because we want to add this angle. Okay, because that negative is saying the same angle over here, but going down. So for quadrant 3, we have pi plus 0.729728. For quadrant 4, you can either find a coterminal angle, so add 2 pi or 360 degrees, or you can refer back to finding a reference angle in quadrant 4. So reference angle in quadrant 4, we would do 360 degrees, or 2 pi, minus the reference angle. Okay, so that would be 2 pi minus 0.729728. Okay, so in quadrant 3, this is approximately 5.55, excuse me, that's this one. Quadrant 4 would be 5.5535, and then quadrant 3 is 3.8713. Okay, so that would be our two thetas that satisfy 3 sine x plus 2 equals 0. Okay, now we want to solve for sine x minus 1 equals 0. So we have sine x equals 1. which is then x equals sine inverse of 1. Okay, so sine inverse of 1, this is in quadrant 1, so sine inverse of 1 is going to give me pi over 2. Okay, so we have 3 answers here. X is either pi over 2, 5.5535, or 3.8713. Okay, so those are the 3 solutions that would satisfy this equation. And then make sure your answer is in radians, since we are given an interval of radians. Alright, so example 4, find all solutions of cosine x times cosine x plus 2 equals 1. Okay, so first we want to use the distributive property. So we want to distribute this cosine x to everything inside the parentheses. So we have cosine squared plus 2 cosine x equals 1. And then we're going to subtract the 1 to the other side. So cosine squared x plus 2 cosine x minus 1 equals 0. Okay, in this case, this is not factorable. So if I was to write it in terms of x, I'd have x squared plus 2x minus 1 equals 0. Okay, so this is not factorable. So when you come into something that's not factorable, we have to use the quadratic equation. Okay, so remember the standard form for a quadratic is ax squared plus bx plus c equals 0. So make sure you have it set equal to 0 before you find a, b, and c. So here we have a is equal to 1, b is equal to 2, and then c is equal to negative 1. And then the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Alright, so then we're going to plug this into the quadratic formula. So I have x equals negative b, so that's going to be negative 2 plus or minus the square root of b squared, so that's 2 squared, minus 4 times a is 1, and c is negative 1, all over 2 times a, which is 1. Alright, so let's simplify. We have negative 2 plus or minus the square root. 2 squared is 4, and then this is going to give me a positive 4 over 2. So I have negative 2 plus or minus the square root of 8 over 2. Okay, the square root of 8 can be simplified. So we have negative 2 plus or minus 2 square roots of 2 over 2. Okay, all of these have a 2. We have a 2 here, here, and then here. So we can simplify that even further. So that's going to simplify down into 1 plus or minus the square root of 2. Okay, and then remember that this is not just x. Okay, this is cosine x. So let me add cosine here. So this means that cosine x equals negative 1 plus or minus the square root of 2. Alright, so also don't forget that cosine has a range of negative 1 to 1. Okay, so when you're trying to decide if we need the plus or minus, if we use the minus, so we have negative 1 minus the square root of 2, that's approximately negative 2.414, which is not in the domain. Not in the range. Okay. So that means the only one we're going to use is the plus. So we have cosine x equals negative 1 plus the square root of 2. Alright, so then we have the inverse function, so x equals cosine inverse of -1 plus the square root of 2. So x is approximately 1.1437. Okay, so this would be in quadrant 1. Okay, so cosine is positive in quadrant 1 and in quadrant 4. Okay, so we need to also find the angle in quadrant 4. So using this as our reference angle, since we're in quadrant 1, quadrant 4's angle would be 360 degrees, or 2 pi, minus our reference angle of 1.1437. So that's approximately 5.1395. Okay, so our answers for our domain of 0 to 2 pi would be 1.1437 and 5.1395. Okay, and I also want to just note, so I did 0 to 2 pi here, but it is not stated in the question what our domain is. So if you needed a domain for all solutions, then you could do 1.1437 plus 2n pi, which is just 2 pi times n, where n is any integer. You could also do plus 360 degrees times n. So you're just finding a coterminal angle with 1.1437. Same thing goes for the 5.1395. So plus 2n pi. That would also find a coterminal angle with this angle. Now make sure that if you are going to use the 360 degrees, that you change this angle from radians to degrees. So this would become 65.5 degrees, and that would be 294.5 degrees, and then plus the 360 in. Okay, so be careful with your radians and degrees. Example 5, so trigonometric identity substitutions. Okay, so we're going to use identities to substitute in and solve this equation. Our interval is in radians, so then our answer is going to be in radians. Alright, so for this, so we have cotan x minus square root of 3 equals cosecant x. Okay, there's nothing here that is factorable. So another step that we are going to use is squaring both sides of the equation. Okay, if we square both sides of the equations, then we have to check our answers. Okay, so must check answers. Alright, so if we square both sides here, so we're going to have cotan x minus square root of 3 times cotan x minus square root of 3 equals cosecant squared x. Alright, so we're going to FOIL this left side. So cotan squared x minus 2 square roots of 3 cotan x plus 3. Okay, and then the right side, if you'll notice that this is an identity. So cosecant squared x is equal to 1 plus cotangent squared x. Okay, and we're using this identity because we have cotangent on the left side, so we want to do something that relates our cosecant with what we have on the left side. So I'm going to replace cosecant squared x with 1 plus cotangent squared x. and then we're going to keep solving from here. So if I subtract cotangent squared x on both sides, I'm going to remove this term. So I have negative 2 square roots of 3 cotangent x plus 3 equals 1, which then gives me negative 2 square roots of 3 of cotangent x equals 1 minus 3, so it's going to give me a negative 2, and then divide both sides by the negative 2 square roots of 3. So we have cotangent x equals negative 2 divided by negative 2 square roots of 3. Okay, so this gives me that cotangent x is equal to 1 over square root of 3, or square root of 3 over 3. Okay, I'm going to stick with this first one. Okay, so if we want to use the inverse function, so we're trying to solve for x, so we have x equals cotangent inverse of 1 over square root of 3. Okay, so recall when you're doing cotan inverse, to put in your calculator, you have to relate it to tan inverse. So our argument here is positive, so we can just directly do tan inverse of 1 over x. So 1 over square root of 3 is going to become square root of 3. Okay, and we don't have to add the 180 this time because our argument was positive. Alright, so tan inverse of square root of 3 is going to give me pi over 3. So this is quadrant 1. Okay, but cotangent is positive in quadrants. So positive in quadrant 1 and quadrant 3. Okay. So to get our reference angle in quadrant 3, we do pi plus our reference angle of pi over 3. Okay? So we have pi plus pi over 3, which is going to give me 4 pi over 3. So this is in quadrant 3. Alright, so these are the two solutions that I solved for. Because we squared in the beginning, we must check our solutions. Okay? So we have to check to make sure that both of these solutions actually work. Okay, so I'm going to check pi over 3 first. So I'm just going to plug this into the original equation. So I have cotangent of pi over 3 minus square root of 3 equals cosecant of pi over 3. Okay, so here cotangent using the reciprocal identities, I have 1 over tangent of pi over 3 minus square root of 3, and then reciprocal for cosecant would be 1 over sine of pi over 3. Okay. So solving this is going to give me negative 2 square roots of 3 over 3 on the left side, and on the right side we have 2 square roots of 3 over 3. Okay, so the left side is negative and the right side is positive, so this does not work. Okay, so pi over 3 cannot be a solution. And this is why we check, because when we square it, we get the positive, okay? But that's not actually the case. So pi over 3 doesn't work, so then we want to check 4 pi over 3. So cotangent of 4 pi over 3 minus the square root of 3 equals cosecant of 4 pi over 3. So again, using the reciprocals. Okay, so this is going to give me negative 2 square roots of 3 over 3, which equals negative 2 square roots of 3 over 3, which is correct, so that works. So our answer is 4 pi over 3. Okay, here at the bottom is just some helps for solving a trig equation. Decide whether the equation is linear or quadratic in form. That's going to come from the exponents that you have. If there's no exponents, then it's linear. If there's an exponent of 2, then it is quadratic. If only one trig function is present, and then solve the equation for that function. If more than one trig function is present, rewrite the equation so that one side equals 0, try to factor, and then apply the zero factor property. If the equation is quadratic in form but not factorable, use the quadratic formula, and then check the solutions are in the desired interval. And then lastly, try using identities to change the form of the equation. It may be helpful to square each side of the equation first. In this case, you have to check for extraneous solutions. Okay, so this last one is what we did here to check to make sure that our solutions actually did work in this interval.